The African continent houses a rapidly expanding digital economy, but it faces a severe physical bottleneck. As of today, the region holds a mere 0.6% of global operational data center capacity. Because of this deficit, the vast majority of domestically generated data must be routed, processed, and hosted offshore. This architecture introduces high network latency and creates distinct geostrategic vulnerabilities surrounding national data sovereignty. The root cause of this deficit is infrastructural. The traditional Western approach to data relies on centralized hyperscale facilities, massive physical footprints that demand enormous, uninterrupted supplies of baseload electricity to function. In many sub-Saharan regions, outside of a few specific urban hubs, the reliability of the electrical grid frequently hovers below 60%. To prevent their servers from going dark during outages, operators are forced to run heavy diesel generation plants for continuous baseload operation rather than just emergency backup. This reliance on diesel drives energy expenditures up to a staggering 55% to 65% of total operating costs. This chart highlights market projections for African data centers versus edge computing. To bypass grid failures, the market is pivoting from centralized hubs. The broader data center market shows 14.46% growth, but localized edge computing is accelerating at 33.6%, aggressively favoring decentralized processing. Attempting to replicate Western hyperscale architecture here is financially and operationally unviable. To scale effectively, the Internet's physical layer must be engineered entirely from the ground up for the local context. Bypassing the grid bottleneck requires a first principles approach. We must engineer an off-grid micro data center, layer by layer, starting with the physical envelope. The first constraint is structural. The building envelope needs to provide security and insulation, but traditional steel and concrete carries a massive embodied carbon footprint. Instead, the walls can be fabricated using an advanced composite mix of limestone calcined clay cement, known as LC3, and bamboo. LC3 technology blends lower carbon limestone and calcined clay, replacing the highly pollutant clinker used in standard cement. That single material substitution reduces carbon dioxide emissions by up to 40%. By utilizing bamboo bioconcrete as the structural aggregate, the facility integrates a fast-growing, highly renewable resource that naturally sequesters carbon. This table compares the physical properties of traditional concrete against the bamboo composite. First, the density of the bamboo composite sits at roughly a third of traditional concrete. This drastically reduces the structural foundational load, allowing these modular edge nodes to be deployed rapidly across uneven, variable terrain. Second, its incredibly low thermal conductivity provides superior inherent insulation, shielding the sensitive server equipment inside from extreme equatorial heat. That insulation directly addresses the second major engineering constraint, operational cooling. High-density AI workloads process multiple tasks in parallel on high-powered GPUs, generating extreme internal heat profiles. In remote locations, managing that thermal output with traditional active HVAC chillers drains an enormous amount of power, requiring immense and expensive battery storage setups to keep the facility online. The solution is thermodynamic. By applying engineered photonic coatings to the facility's roof, we deploy passive daytime radiative cooling, or PDRC. These specialized surfaces reflect up to 98.4% of incoming shortwave solar radiation, preventing the structure from absorbing ambient heat. Simultaneously, the material takes the internal heat generated by the servers and emits it upward as long-wave infrared radiation. It emits this thermal energy precisely within the specific atmospheric transparency window of 8 to 13 micrometers. Because the Earth's atmosphere is completely transparent to these wavelengths, the heat bypasses absorption entirely and dumps directly into the ambient freeze of outer space.
Integrating bamboo bioconcrete for insulation with PDRC surfaces achieves autonomous thermal regulation. The localized solar arrays can dedicate their power directly to the AI compute workloads without the parasitic energy drain of air conditioning. Solving the structural and power constraints of the physical node leaves the third major barrier, the connectivity void. Terrestrial fiber lines are expanding inland from subsea cables, but physically trenching that fiber to remote agricultural zones and rural communities remains economically unviable. The solution is the rapid migration of the core transport layer into low Earth orbit. New satellite constellations connect to one another, forming an active orbital mesh network above the continent. Systems like the Kepler Ether network bypass congested legacy radio frequencies. They utilize optical intersatellite links, creating an orbital fiber optic backbone using secure lasers in the vacuum of space. Remote enterprise nodes can connect directly to this optical backbone. This guarantees sub-second end-to-end latency at bidirectional speeds up to 2.5 gigabits per second, circumventing the need for localized terrestrial fiber lines. But routing high-speed data through space introduces the next engineering step. Instead of just relaying data, you can process complex AI analytics directly in orbit before downlinking it to Earth. The primary barrier to doing this is a severe aerospace dilemma known as the thermos problem. Space is an absolute vacuum. Because there is no air or fluid, it acts as the ultimate thermal insulator. You cannot use traditional convective fans to cool hardware. Placing high-performance computing equipment inside a pressurized satellite module leads to rapid thermal runaway and catastrophic hardware failure. An aerospace entity called Sophia Space engineered a solution to this barrier via its tile architecture. Each modular compute unit is designed as an ultra-thin slab, measuring exactly 1 square meter in surface area, but only 1 centimeter thick. One side of the flat form factor features an integrated solar array, generating its own autonomous power. Inside, NVIDIA processors are mounted directly against a massive aluminum alloy passive heat spreader on the reverse side. This extreme surface area to volume ratio efficiently radiates generative heat straight into the cold of deep space. By redesigning the hardware so the thermal management system is the architecture itself, 92% of the generated solar power is dedicated directly to compute processing. This enables massive, zero-emission data centers to operate continuously in orbit. Synthesizing sustainable terrestrial nodes with orbital networks solves unique operational challenges. In agriculture, edge-equipped machinery runs local computer vision for precise autonomous tasks. The generated metadata is beamed to an off-grid bamboo node, which uses an optical satellite uplink to synchronize the intelligence globally. Because this data pipeline bypasses terrestrial fiber and the national grid, regional insights remain accessible even during localized infrastructure damage or network outages. Currently, 67% of the continent's data center operators view acquiring skilled engineering staff as their primary hurdle. This diagram outlines the interdisciplinary skill matrix required for the African edge economy. This deployment requires a fundamental shift in technical education, demanding mastery of the strict intersections of digital infrastructure, renewable energy, and sustainable construction. The modern edge technician must securely route complex network protocols while managing the extreme thermal dynamics of an AI server rack, powered by localized solar arrays and housed in low-carbon bamboo biopond meat. Aligning ecological building standards with orbital compute establishes a high-performance model tailored to the continent's unique constraints. Ultimately, this orbital-terrestrial synergy provides a highly resilient, unbreakable blueprint to guide the global transition toward green digital infrastructure.